Here we have our first lemma, lemma 1. And I'm not going to prove this lemma. All I want to do is show you why it's true. And I'm going to show you why it's true with an example. Remember that an example is not a proof, but it can show you why something is true. Okay. So the first line in lemma 1 says, suppose that in the graph G prime, the number of vertices of odd degree is m. Okay, so m is the number of vertices of odd degree. So the number of odd degree vertices. So let's go through and count the number of odd degree vertices. The first way to do that, the first step to doing that would be to just determine the degrees of each of the vertices. So this, starting with this vertex right here, remember the degree is the number of edges adjacent to that vertex. Another way of thinking of that is just the number of edges that touch that vertex. So this vertex touches 1, 2, 3, so the degree is 3. This vertex touches 1, 2, 3, so the degree is 3. This vertex, 1, 2, 3, degree is 3. 1, 2, 3, degree is 3. Let's see, 1, 2, degree is 2. 1, 2, degree is 2. 1, 2, 3, degree is 3. And here the degree is 1. All right, so how many, so remember, m is the number or the amount of vertices of odd degree. So how many vertices of odd degree do we have? Let's see. 1, 2, 3, 4, 5, 6. So m is 6. 6 is the number of vertices of odd degree. So m is 6 in this case, not for all cases. Remember, with a lemma, we're trying to capture all possible cases. With a lemma or a theorem, we're trying to capture all possible cases. I'm just showing you right now that is true with an example. All right, so now going to this second line here, right, we see that this thing right here, if UV is not an edge, remember that when we write this, this means that U and V are connected by an edge. Right, so this, if UV is not, right, is not an edge in G prime, and you can see that's the case, right? It's not an edge in G prime. And the degree of U is odd. Let's see, remember this was 3. The degree of U is odd. Okay, that meets that criteria. And the degree of V is odd. That was 1, so that meets that criteria. Then the graph G, that is exactly the same as G prime. And notice that these two graphs, G and G prime, are in fact exactly the same graph, except for in G, we've added this edge right here between U and V. So if we add an edge between two vertices that don't have an edge between them to create a new graph, and both of those vertices that we added the edge between had odd degree, then the number of vertices of odd degree goes down by 2. Right? So if we were to go through and count the number of vertices of odd degree over here, we'd find that it was 4. Number of vertices of odd degree over here we found was 6, right? But now if we count them over here, it's going to be 4. So why is that? Right? Why is that? So notice over here the degree, right, was 3 and the degree was 1. If we add an edge between them, taking us over to G, right, now we have 1, 2, 3, 4. So that goes up to 4. 4. So it's no longer a vertex of odd degree. It goes, so the number of vertices of odd degree goes down by 1 for this one. And now V goes from degree 1 to 1, 2, right? So degree equals 2. Right, so we add that edge between them, right? It makes sense that the degree would go up 1. If they both were odd, odd plus 1 is even, right? So the number of vertices of odd degree goes down by 2. So in other words, if M in G prime is 6, then the number of vertices of odd degree equals 6 minus 2, or 4, otherwise known as M minus 2. So the M, right, the M is something defined for G prime, not for G. So whatever M is for G prime, if you have this situation where you draw an edge between two odd degree vertices that don't have an edge between them already, then the number of vertices of odd degree in G goes down by 2.